I'm so glad that you're here today. We are doing the second part of geometric sequences as exponential functions. So yay, let's begin. Let's get into this. Let's start off. So this is important. You need to write this down. And I'm trying to think. No, of course I didn't give you a spot to write this down in. So yeah, squeeze it in somewhere, okay? So let's look at this. Right here, a to the nth power. This is basically, it's the value of the nth term. Okay. Here is the value of the first term. So see how you have n. So this right here, this is basically like describing, right? It describes what term. So we know that m is actually, n is the number, how would you say that? The number of terms? Yes. Or it's the order in which it, how did I phrase it before, Miss Tiva?
What? N?
Yeah, the nth term.
Picture of it. Let me just.
Let's see, I have it right here. N is any positive integer. These are my little cheat sheets.
It's the number of terms.
Yeah, it's the number of terms, yeah. So n is the number of terms. We'll just leave it at that. And then R is our common ratio. Okay, so a couple of things that were brought up last time, thanks to Tiva, is that if we have something like a to the power of n, that is not the same as a subset n, right? This actually means this is an exponent, right? It tells you how many times you're going to multiply it. And this is more of just a description. When we use a subscript, that just kind of is more of a description. Let's see if I can spell description. Okay. I think the other thing that we need to take into place is the whole just keep in mind that the common ratio is related to but not equal to. So related to but not equal to the rate of change in growth and decay. Okay? So you remember when we were talking about growth and decay and we had like 1 minus r? Unfortunately, they do call it the same variable, which makes it a little confusing, but it's not. The rate of change in growth and decay. Okay, let's go ahead and let's look at this example right here. We're going to find the nth term of this. Was this the one? No. Let's go back. Was that it? Oh, yeah, it is it. Okay. Oh, this is it. So we want to write an equation. So we're writing an equation for the nth term of the geometric sequence. Let's go ahead and rewrite what we just had before. AN is equal to A1, right? And that's going to be times R to the power of n minus 1. So for the nth term, that means that we don't know what n is. That's going to remain that way. And then here, we do know A1, right? What is A1 going to be? 1. A1 is 1. And like this one, that's A2. That's equal to negative 2, right? So the 2 there, that just tells you like where it is in the sequence. So we do know what A1 is. It's 1. And then when we look at this common ratio, remember the formula is to take the second term and divide it by the first. So our second term is negative 2, and we divide by 1, and we end up with negative 2. So notice in here, that each time we're just multiplying by -2 every single time. And so that's what's going to go in here. We don't know what n is. And there's our formula. Easy?
Yeah.
Awesome. Any questions? Okay. Hello, boys and girls. Welcome. We are here on example 3b. We're going to find the nth term. And specifically, they want the 12th term of the geometric sequence. So it's the same sequence that we had before. Remember, our formula was an equals, it was like 1 times -2 to the power of, it was like what?
N minus.
Yes, thank you. So what is, when they say the 12th term, what does that actually mean?
To fill that in for n.
Exactly, n is equal to 12. So what we're going to do is we're going to rewrite everything except for n. And I'm going to put a 12 right there. And so, let's see if it'll do it. Boop. No? Come on. Okay. So I put a 12 right here and then a 12 right here. Okay. So once we do that, we can actually just plug it into our calculator. I think that's where we were at, right?
Yes.
And we were kind of talking about how, you know, why didn't I put like A12 in there? Number one, Desmos doesn't really understand anything unless it's X or Y. It makes you put in like sliders. So sometimes if we just want the value, just type in 1 minus 2. And then I'm going to put in that exponent thing. I'm using like shift like 6, which brings it up, but you could use the little keyboard on there. And then I noticed that if you want to put something like long in the exponent, you really have to put parentheses. This is just how I got it to work. 12 minus 1. Of course, you could just put 11 because, you know, that's 12 minus 1. And there's your number, right? And so our 12th term is actually going to be -2048. And so that's way easier than doing it 12 times, right? Maybe, maybe not.
Yeah.
Okay. So, and of course, like if they wanted the 1000th time, it's definitely easier than doing it 1,000 times. Kind of wasted time. So there we are with that one. Let's go ahead and let me give you your last problem for today, I believe. Let's look at, any questions on this one?
No.
Nope, pretty straightforward. All right, then let's go ahead and let's look at the next one here. You know, I just need this a little higher. There we go. All right, so we're going to be graphing a geometric sequence. Here we have a 50-pound ice sculpture that's melting at a rate in which 80% of its weight remains each hour. Draw a graph to represent how many pounds of the sculpture is left at each hour. Have you ever seen like an ice sculpture up close?
Yeah.
Yeah. Usually like at weddings or something.
Yeah. I saw that at a wedding one time. It was big.
Yeah, because then they melt and, you know. Yeah, I've seen some. So here we go. I'm going to just do the basic one. AN is equal to the first term, A1, times R to the power of N minus 1. So help me out, Tiva. Any ideas what I can put in?
Well, like, wouldn't we have to do like the growth and decay, whatever, which one it would be?
There is a relationship, right? Because these are exponential.
Mm-hmm.
So, but like, for example, it says it's melting. So what do you think this is going to be, growth or decay?
Okay.
It's going to be decay, right? Let's address this. Let's just kind of start at the beginning. We have a 50-pound ice sculpture. So what's that going to be?
That's the initial, right?
Yeah, that's your initial value. That's your very first term. So definitely going to plug in 50 right there. Okay. Then it says it's melting at a rate in which 80% of its weight remains each hour. So is this saying that it's decaying at a rate of 80%? Or is it saying that we're multiplying the initial weight by 80%? What do you think? Because that's like that subtle little stuff, right?
80%. But it would still be decaying because 20% of its weight is still not there.
Okay, you're onto something with that 20%. Okay. Let me just, it doesn't have the words rate of decay, right? It says it's melting at a rate in which 80% of the weight remains. So let me just kind of start off with something really simple, right? If I had a 100-pound ice sculpture and that's each hour, right? So that was at 2 p.m. So then at 3 p.m., how much of that sculpture would still be there? Instead of 100 pounds, you would have only.
Would be.
Okay, 80%.
99 point.
Girl, you're making this way harder than it is. Okay, 80% of 100 is 80.
Mm-hmm.
So here's the deal. If your ice sculpture was 100 pounds at 2 p.m., then at 3 p.m., you would only have 80 pounds of it. Does that seem logical to you?
Yes, but like how? I'm just confused about how it gets to that point.
How it gets to that? So I think what you're saying is, and correct me if I'm wrong, you really want to know what the rate of decay is, right?
I feel like.
Because you want to tie it into what we learned before, the exponential, right? Okay, because remember exponential was something like this. It was like, here's your initial, right? And then it was 1 minus r to the power of t, right?
Yes.
And so there is that relationship. There is that relationship. The thing is, remember how we would calculate for this unit, we talked about the common ratio. The common ratio is r, right? That's everything that's inside of the parentheses. And that's one thing I think that may be a little bit confusing because they use R for the same thing, right? They use R, but here, this is really your rate of change, right? That's your rate of decay. And here they use the same variable, but it's for your common ratio, which are two different things. So they really shouldn't do that because that's confusing. Yes? Okay. But keep in mind that those are two different things. The common ratio, as we talked about in the last video, is the second term. Let me kind of is the second term divided by the first term, right?
Mm-hmm.
And so that's 80 divided by 100, which actually, if you put it in your calculator, ends up being 0.8, right?
Mm-hmm.
Which is the same as what percentage?
80%.
80%. Okay. So what this is your common ratio. Now here's the deal. If I said, what is your rate of decay when you're multiplying everything by 0.8, right? Because that's what's going to be in here is 0.8. If these two are equal, right? And somebody out there is going, oh, dear God, just no. Don't make it this hard. What is R? What do I have to do to solve for R?
Subtract by 1.
Subtract by 1. Okay. This is the additive inverse. I got negative R equals, and what is 0.8 minus 1?
Negative 0.2.
Negative 0.2, which is, now I want to get R to be positive, so what do I have to do?
Divide by negative.
Sure. Divide, multiply by negative, don't matter. A negative divided by a negative is a positive, and a negative divided by a negative is a positive. And so what is your rate of decay?
Rate of decay?
Mm-hmm. This is the same as what percentage?
20, right?
20%. This has a rate of decay of 20%. And I mean, if you think about it, we start off with a 100-pound ice sculpture, right? 20 pounds of it melted away. That's your rate of decay, right? So do you see that difference between the common ratio is the number that we have to multiply by it. So that's multiplying by 0.8. The rate of decay is how much of it is actually going away. Well, it's 20% that's going away. Do you see the relationship between the two?
Yeah.
Okay, cool. Now let's go back to the problem. So we have, we've got 50 here as our initial, our first term. We have point A as our common ratio. And then we need to figure out what n is. Is that a possibility? Well, no, not yet, because we're going to come up with a bunch of n's. And then, of course, this right here. So this is as far as we can take it. And what I'm going to do, remember that we said it was kind of similar to y being right there. And then we have 50 times 0.8 to the power of x minus 1, right?
Mm-hmm.
Something like that. You could do it like that. But you know, okay. So let's go ahead and let's put in x and y. Okay. And I'm going to, let's see. I'm going to put it into Desmos. Let's get some stuff. So I went ahead and I put it into Desmos, typed it in. I want to make a table out of it, right? So I select the little gear. And then I select the table. And it lets me move it to a table, right? Not really interested in negative time. So I'm just going to ignore those. But here I'm going to put in, and I'm probably going to put it until about 6. So I've got 3, 4, 5, and 6. And there we are. So I've got my little table all nice and dandy. I'm going to transfer it over here into my notes so that I have them forever and ever. Okay. 0, 1, 2, 3, 4, 5, 6. I'm going to put in 62.5. Wait. Oh, I don't want 0. I really want, that's the kind of, okay, so when we get into sequences, there's like only like the first. You can't have a 0 one. So we really kind of just ignore that one, right? I will finish putting it in, but we are going to ignore that one. That's not really going to go on the graph. We start off with a 50-pound sculpture, then it melts down to 40, then to 32, then to 25.6, 20.48, and 16.384. So just to kind of go back to this, I mean, remember that you started off with a 50-pound ice sculpture, right? So why am I going to include 62.5 pounds? You can't go back into time, right? Okay, so that's my point with that one. Let's go ahead and we're just going to like sketch this out here. If I look at this, let me move this out of the way. Let's see, we've got 1, 2, 3, 4, 5. So each one is worth 1. And then here I've got 1, 2, 3, 4. 20 divided by 4 will give me 5. So each one is worth 5, right?
Yes, ma'am.
Okay, we got 1. We got 50. Look good?
Yeah.
Okay. And then I'll make it a little darker so y'all can see it. Okay. And then we got 2 and we have 40. 3 and 32. So each one's worth about, let's see, that's 30. This is 35. Maybe it's a little closer to 30. Next one is 4 and 25.6. So 4 and then 20, 25, and that's like really close. I'm just gonna make it like that. Next one is really close to 25 and 20, slightly above. And then 6 is 16, so that's 15 and just like a little bit more. And so we definitely get the idea what it's starting to look like, right? It's kind of like right here, and then it just starts melting, and melting.
Yeah.
Okay, so when does it melt like the fastest? In the beginning or as time goes along?
I think in the beginning, because it went from 50 to 40.
Exactly. You've got the biggest gap there, right? You've got like 50 to 40. So it like lost 10 pounds right there, right? And then here, it doesn't quite lose 10 pounds. It's more like 8 pounds, right? So definitely, I would agree with that. That in the very, very beginning, you get the most amount of loss on that sculpture. Okay. So any questions on this one?
No, this one made sense.
Yay. Let's double check and see something really. Okay, so for those out of you in Cyberland, you go ahead, you can private message me kind of where you're at, 1, 2, 3, 4, 5. If you're at a 3 or lower, come see me, okay, so that we can clarify that and get that definitely at a higher level of understanding. I hope it was pretty straightforward. And to the next day, we should probably have like some practice, some guided practice on this. Have a great day. Toodles.